Okay, let's dive right in. Welcome back to the deep dive, and a big hello if you're joining us from the AI of Think channel. Have you ever stopped to really think about the invisible instructions, the silent procedures that are basically powering so much of the tech we use every day, especially, when we talk about AI?
It's funny, we almost never do, right? We see the end result, the cool stuff AI does.
Yeah.
Maybe it's a brilliant move in a game or a recommendation that's spot on or, I don't know, self-driving car doing its thing. But the actual how behind it, that usually stays hidden.
Absolutely. And that how is all built on algorithms. So in this deep dive, we really want to pull back the curtain on those core building blocks and the
Yeah.
algorithms and explore how they let AI actually solve problems. We'll look at, what they fundamentally are, how they're used to map out different possibilities, how they deal with the messiness of the real world. And we'll touch on the algorithms driving the AI wave right now.
Yeah, and there's this interesting thing here. It's often called the AI effect. It's this sort of tendency, when an AI application gets really successful, becomes totally commonplace, we just kind of stop seeing it as AI.
Huh. Like what?
Well, think about route planning in your GPS app, or those huge systems that manage complex logistics schedules for companies. I mean, these were cutting-edge AI problems once.
But now, they're just tools we use every day. The AI label seems to constantly shift to the next big challenge, the thing we haven't solved yet. The solved stuff starts to feel almost, normal.
Yeah, it's, AI is always defined by what it can't quite do yet.
Yeah.
But okay, behind everything that does work, whether we still call it AI or not, there are algorithms.
Mhm.
So let's start right at the beginning. Fundamentally, what is an algorithm?
Yeah, super simple at its core. An algorithm is basically a procedure. It's just a defined sequence of operations, steps you follow to get something done or solve a problem.
And it's not just for computers or math, right? We use them constantly, like following a recipe, step one, step two. Exactly. Or giving directions. To turn left, then right, go 3 blocks. That's an algorithm.
Even putting together IKEA furniture with those diagrams, okay, maybe sometimes frustrating ones, but still.
Still an algorithm,
Yeah.
a sequence of actions to get to a goal, like a finished bookshelf. And this simple idea, it's absolutely crucial. For any system, really a person, a machine, whatever, to reliably do something, it needs a clear process. No algorithms, no structured problem solving. Things would be chaotic.
Okay, so algorithms are the basic instructions. How does AI actually use them to tackle problems? Let's maybe look at some of those classic AI challenges from the early days.
Right. A really big focus early on was on problems that involved planning, finding a path to get to some goal. And this is where concepts like state space search come in. They were fundamental.
State space search. Okay, that sounds a bit technical. What does that actually mean?
Imagine any problem as just a whole set of possible situations, or states. You start in one state at the beginning, and you want to reach a specific goal state at the end. State space search algorithms basically explore all the possible actions you could take from where you are now and what new situations or states those actions would lead to. It's like they're mapping out every single potential path forward. Think of exploring all the branches on a tree or all the connections on a big graph, trying to find a sequence of steps that gets you from the start to the finish line.
Okay, I think I'm getting it. Sort of like navigating a maze. You're at the entrance, you try one turn, see where it goes, maybe backtrack, try another until you find the exit.
That's a really good way to visualize it.
Yeah.
Or think about optimizing delivery routes for a logistics company, finding the absolute best sequence of stops to save time or fuel, or scheduling jobs on a factory floor for peak efficiency, or even just figuring out how a robot arm should move to grab something without bumping into anything else. All of these can be seen as finding a path through a space of possible situations.
And the material mentioned a really relatable example games, especially those competitive ones, hostile games, they're sometimes called, like checkers or chess or Go. AI famously uses these search methods in games.
Oh yeah, games are perfect test cases. Why? Because the rules are totally clear, and the goal winning is obvious. So AI uses these search algorithms to look ahead, right? Exploring its possible moves, the opponent's possible counter moves, then its next move, and so on. A really classic technique is the min-max approach. Basically, the AI assumes its opponent will always make the move that's worst for the AI. So the AI tries to pick the move that minimizes that potential damage, that maximum loss.
Wow. Okay. So it's not just planning its own move, but it's constantly thinking, what's the best thing my opponent can do to mess me up? And trying to find the safest route through that potential conflict. That sounds like it would take a ton of computation, especially in really complex games like chess or Go.
Oh, absolutely. The number of possible game states in chess, and especially Go, is just astronomically huge. It's mind-boggling. And that's exactly why efficiency tricks are so important. Things like alpha-beta pruning.
Alpha-beta pruning. Sounds like something from gardening class.
Huh. Different kind of pruning. In this context, it's about being smart and cutting off entire branches of that future possibility tree. If the AI is exploring a sequence of moves and realizes, hey, if I go down this path, my opponent can force a situation that's already worse than another option I know I have, then it doesn't need to explore that whole branch any further. It just prunes it, cuts it off, saves an enormous amount of calculation.
Got it. So it's not just blindly checking every single possibility. It uses logic based on what it's already seen and assuming the opponent plays optimally to ignore paths that definitely won't lead to the best outcome. Clever. Okay, so these search algorithms are super powerful when the problem is well-defined, like a game, even if the number of possibilities is massive. But what about, well, the real world? Life isn't usually a neat game board. It's messy, things are uncertain, sometimes you don't even know all the rules or possibilities. How do algorithms cope with that kind of complexity?
Right, that's a huge challenge, and that's where a different family of algorithms often comes in, things generally called local search algorithms. Now, unlike that exhaustive search we were just talking about, local search doesn't try to map out everything right from the start. Instead, it begins from whatever the current situation is, which might be far from perfect, and it just tries to make small improvements. It does this by looking only at the options immediately nearby, in the local neighborhood of the current state.
Okay, like, imagine you're trying to find the highest peak in a foggy mountain range. You can't see the whole map, you can only see the ground right around you, so you just keep taking steps uphill from where you are.
That's a perfect analogy. You're trying to improve things based only on local information. But, in a complex landscape, how do you decide which uphill step is the best one to take? Especially if there are several options. Or maybe the best immediate step leads you to a small hill instead of the highest mountain overall.
Yeah, good point.
That's where these algorithms often rely heavily on something called heuristics.
Heuristics, right? Those are like educated guesses, rules of thumb.
Exactly. A heuristic is basically a strategy or maybe a shortcut or a piece of knowledge that isn't guaranteed to find the absolute mathematically perfect best solution every single time, but it's likely to find a good solution, or at least push the search in a promising direction much faster than trying to calculate everything perfectly. There are essential guides for local search when the perfect path isn't obvious or it's just too complex to figure out. They give you direction in fuzzy situations.
Okay, and where do we see these kinds of algorithms, local search using heuristics being used? What are some examples?
Well, the material mentions things like trying to identify potential insurance fraud or helping doctors with medical diagnosis.
Why those areas specifically?
Because think about it, those situations involve a huge number of possible factors. Often you have incomplete or uncertain information. And the rules connecting symptoms to diseases or transaction patterns to fraud aren't always 100% fixed like the rules of chess. They're probabilistic, complex.
Right. Making a diagnosis isn't just following a checklist. It involves weighing likelihoods, thinking about interactions, using experience, which sounds a lot like human heuristics, actually.
It really is.
Yeah.
So an AI system helping with diagnosis might use heuristics, maybe based on statistical patterns or medical knowledge, to suggest which tests are most likely to be informative based on the initial symptoms. It helps guide its search through the vast space of possible conditions more effectively. Same idea with fraud detection. The algorithms use heuristics, often learned from patterns in millions of past transactions, to flag new ones that look suspicious. It guides their search for anomalies in this massive flood of data. Without those rules of thumb, it would be totally overwhelming.
The source material also mentioned expert systems here, didn't it, as an earlier approach?
Yes, that's right. Expert systems were a really important phase in AI history. They were specifically designed to try and capture human expertise. They did this by using large sets of if-then rules, like if the patient has symptom A, aiding D symptom B, then consider condition X. These rules were often painstakingly gathered from human experts in a specific field.
So they were basically trying to hard code human heuristics.
In a way, yes. They were formalizing that expert knowledge into a system. And they could be quite effective within their narrow specific domains using those rules to solve problems or offer advice.
But they ran into problems.
They did, significant ones. They really struggled when faced with situations that weren't covered by their explicit rules. They often had trouble dealing with conflicting rules or uncertainty, and just maintaining and updating those massive rule bases as knowledge changed or new situations arose. It was incredibly difficult and brittle. The real world is just too dynamic and complex to capture perfectly in static rules. That's a big part of why AI research started moving more towards approaches that could learn and adapt.
Which neatly brings us towards the kinds of algorithms that are really driving a lot of the AI buzz today. The ones that feel almost, well, magical sometimes. The ones that seem to just learn.
Right, you're talking about algorithms that learn directly from data. And this is a really fundamental shift from those classical algorithms we've been discussing.
Because the classical ones, even the ones using heuristics, are ultimately following steps or rules that a human explicitly programmed or designed into them, right?
Precisely. With learning algorithms, it's different. You don't sit down and write out the exact step-by-step instructions for, say, recognizing a cat in a photo. Instead, you feed the algorithm massive amounts of examples. Thousands, millions of pictures labeled cat or not cat, or pairs of sentences in different languages for translation, or hours of spoken audio with transcripts. And the algorithm itself analyzes all that data and learns to identify the patterns, the correlations, the underlying features. It essentially figures out how to do the task from the examples.
Wow, that's a huge conceptual leap. They're not following rules we give them. They're deriving the rules, or something like rules themselves, from the data.
Absolutely, and that's why they've become so crucial for tasks that are easy for humans but incredibly hard to describe with explicit rules. I mean, how would you even begin to write a step-by-step algorithm to recognize your friend's face from any angle in any lighting? Or to understand the sarcasm or emotion in a sentence? It's almost impossible with fixed rules. Learning algorithms, especially the deep learning models that are so popular now, are specifically designed to find those incredibly subtle, complex patterns within vast amounts of data that let them tackle things like image recognition, natural language understanding, and speech processing with, frankly, remarkable results.
It really is fascinating how these systems build their own kind of internal understanding of the world just based on exposure to information. And hey, if you're finding this whole exploration of AI's algorithmic engine as interesting as we do, and you want to keep digging into this stuff, make sure you're part of the conversation over on the AI of Think channel. That's really the place where we unpack these ideas together and look at what's happening next in AI.
Definitely. If you're curious about how AI works and how it's changing things, algorithm by algorithm, that's the community to join.
So we've covered quite a bit of ground here. We started with the simple idea of an algorithm as just a procedure. Then we looked at how classical AI uses search techniques to map out possibilities in well-defined spaces. Then we saw how AI tackles the real world's messiness using local search guided by heuristics, those useful rules of thumb. And finally, we touched on how the current wave of AI uses algorithms that learn directly from huge data sets to do things that were unthinkable with older methods.
Yeah, and throughout it all, we see how these algorithms are often the hidden power behind tools that become so normal, they've succumbed to that AI effect we mentioned. Your GPS navigation, complex scheduling systems, spam filters, recommendation engines, they're all running on algorithms, working away quietly.
And I think understanding this, realizing that even the most sophisticated AI is built on these fundamental ideas, computational processes, whether they're explicitly programmed or learned from data, it really helps demystify the whole thing, doesn't it? It shows AI isn't some kind of black magic. It's just incredibly clever, very complex, but ultimately structured ways of solving problems using algorithms.
And that leads to a really interesting thought, especially as these algorithms get more and more powerful, as they become capable of learning, adapting, making really complex decisions based on data at a scale we can barely comprehend. It really makes you wonder, doesn't it? How does our own role change? As AI takes on more tasks that used to need our specific human problem-solving skills, our ways of gathering knowledge, how do we need to evolve in how we understand and interact with the world?
That is a big question to chew on as AI keeps advancing. How do we leverage these tools while also emphasizing our unique human intelligence, our creativity, our critical thinking in a world increasingly full of powerful algorithms?
Definitely something to keep thinking about.
Well, thank you so much for joining us on this deep dive into the algorithms behind AI. We really hope it gave you a clearer picture of the smart procedures running so much of the tech around us. If you found this useful, please do share this deep dive with friends or colleagues who might also be curious about AI. Make sure you join the community over at the AI of Think channel, and of course, please hit that subscribe button so you won't miss our next exploration.